Hello, everyone, and welcome to today's webinar on PHASTA. Thank you for joining the call. My name is Cmake, and I have the pleasure of moderating today's webinar. I would like to introduce our speaker, Dr. Kenneth Jansen. Dr. Jansen is a professor of aerospace engineering and the director of the Aerospace Mechanics Research Center at the University of Colorado. Dr. Ken specializes in bioastronautics and fluid dynamics. He has received numerous awards in his field, and we are honored to have him today to go over the fundamentals of PHASTA, how to set it up and run it for the HPC applications. Let me go over a few housekeeping items before I hand it over to Dr. Ken. Our meeting is scheduled to be around 1 hour. If you have any questions, please type them in the chat box. We will try to answer as many questions as possible at the end. Also, a recorded version of this webinar will be available through the SC22 website and our YouTube channel. Without further ado, let me invite Dr. Ken to start his talk. Welcome, Dr. Ken. The floor is yours.
Thank you. Okay, so I'm going to use two modes. I'm going to start with a presentation and try not to put you to sleep. So we'll try to go through that reasonably quickly. And then I'll do a demo of, of getting acquainted or getting things built up and running some cases. So as you might imagine, a complicated solver like this, we're not going to be able to cover everything in 1 hour, but I think we'll cover enough to get you started. And then I'll supplement this at later times with pointers to additional videos for the more, shall we say, advanced topics. Okay, so as usual, I have too many windows open. So let's start with sharing this PowerPoint, and let's go to the beginning, and I'll put it in presentation mode. Sometimes that basically makes me blind to any of the chat, so but hopefully at least it makes it clear to the screen. Can everyone see my screen?
Yes.
Yes, there are a couple of us watching the chat as well.
But it's in it's not in the presenter view. It's not in the presentation view. It's in the presenter view.
Interesting, because I'm seeing it in the presentation mode. Yeah. Okay. No, I went to sleep. Let's try to wake it back up. Yeah, so I don't actually, maybe I'll try swapping screens and see if that.
Yes, it worked.
Interesting. Now I'm seeing them both well flipped. All right, that's fine. All right, so PHASTA is an acronym. It stands for Parallel Hierarchic Adaptive Stabilized Transient Analysis. Some people will call it PHASTA. We started calling it that, and then I realized that that has an implied arrogance that somehow my CFD solver is faster than everybody else's. So I like PHASTA a lot, so that's the way I pronounce it. But you can call it what you like. Okay, so an outline of the first part of my presentation. There are 24 slides, so we'll hopefully finish this in about 20-ish, 25 minutes and leave time for the demo part. I'll give an introduction to PHASTA and to some of the key things that the project is involved with in terms of HPC. I'll then write down at least the compressible flow equations. If you haven't had a course in fluid dynamics, those are probably going to be, Greek to you. But I think at least we need to see what they look like. And then those are partial differential equations. So we need a method to discretize them. We're going to show a finite element discretization of them. And then I'm going to dive into what are the HPC aspects of PHASTA? That is, how do we make it amenable to a high performance computer, and document a little bit on past parallel performance. I'm only going to spend time on a couple of applications. There are many, many more, and I can probably make available papers if you want to see different application areas. But my guess is, it'll be enough that we'll see what it's interested in. Then we're going to leave the presentation mode and go to GitHub, where we will download test cases, download the code, build it, run it, do a little bit of visualization on it, have some discussion of inputs and outputs, and then we'll just see where we're at that point. Okay, so PHASTA is part of 2 exascale early science projects for the Aurora machine that's being built at Argonne. So the first one is a raw simulation project that's just trying to take CFD to exascale computing, and those are my co-PIs on that project. It's also part of a data science project where we think of PHASTA as really being a very, very large data stream, and we ask the question, can we do more in terms of data analysis of that data stream, and then use it in machine learning as well. So you can see more about this if you like at that link, Aurora ALCF. Okay, one slide on introduction to CFD. And really, I'm really talking about unstructured grid CFD here. And I apologize, I have a big monitor that's above the computer that has my camera. So that probably means that if you're looking at my video, you're often looking at my nose because I'm looking at the larger monitor's screen. That's just, I guess everybody knows that happens in Zoom these days. Anyway, so PHASTA is an unstructured grid solver, and that comes with advantages. That means that because it uses an unstructured grid, it's very easy to handle very complex geometry. And it's also relatively easy to adapt the mesh, the finite element discretization mesh. We put points and connections in locations, and we can refine them to be whatever we want easily. The downside to that is that the method is the discretization method is more complicated and more computational effort per point. And it also means that there are, actually I would say for what we need to do, the post-processing is not any more difficult. You can load it into ParaView or other visualization package and look at it. But this is sort of the truth in advertising and giving you the general view of CFD unstructured versus structured grid CFD, which you will also see in the literature. So popular unstructured grid methods are finite volume, discontinuous Galerkin, and stabilized finite element method. We're only going to focus on the last one, which is robust, minimally dissipative, and can be made higher order easily. That's why we like it. Okay, so one slide on equations. The equations have simple principles. That is, in a continuum level, the compressible equations need to conserve mass, conserve momentum, which is a vector. So there's really 3 equations in the second box, and conserve energy. Lots of symbols, lots of terms. Those that are interested, again, we can provide papers. Just a little bit of, for notational compactness, I'm not writing partial derivatives everywhere, but when it's a partial derivative with respect to t, it has a lowercase comma t. When it's a partial derivative with respect to x, y, or z, that would be x1, x2, x3. We index that with the letter I. And obviously, well, not obviously, I'll try not to say obviously, because it's obvious to people who study this all the time, but not obvious to people who see it for the first time. UI is velocity, rho is density. Well, UI is the 1, 2, and 3 velocity components because velocity can be in 3 dimensions. P is pressure. I'm not going to bother introducing all the symbols, but those are the big ones, shall we say, or the important ones. Okay. Those equations need what we call constitutive laws. That is ways in which those different properties are connected. And if you've had a course in chemistry, you know about an ideal gas law, which relates pressure, temperature, and density. That's one type of constitutive law. We're dealing with viscous equations, so we need also a relationship between the viscous stresses and the velocity gradients. And we will usually get those from a Newtonian viscous law. Or if there is turbulence, then we may have a turbulence model which augments that. And then ultimately there is heat flux. Again, super high level. Coming back, putting all those equations into a vector system, they're ultimately conservation of a vector u plus the divergence of that vector minus some source equals to 0. And this is breaking that F vector out into pieces that map back to the equations from before. Again, not going to go into much detail about this. The finite element operators that we're going to describe very shortly work with discrete forms of those operators. There's a discrete linear operator L, quasi-linear operator, it's not really linear. And we'll also have further things like the ith Euler-Jacobian matrix AI and the diffusivity matrix Kij. And if we change variables from u to y, we have this change of variables metric A0. But ultimately, what the takeaway from this slide really is that I can write my whole PDE system as some operator L times some variable vector y equals S. That's important because when I go to write my finite element discretization, and again, you can skip over the first 4 bullets and only pay attention to the last one. Finite elements basically takes that PDE, dots it with a weight vector W, integrates that over the domain that we want a solution, and that is the second to last boxed term, which is the Galerkin weak form. That's not a stable formulation, so we have to add this second term or stabilization term to it. So this in one slide is the finite element stabilization. I included the definition of the function spaces because I'm told that some of you out there have an applied math background. And if you don't have that, there's no way I'm going to teach you that in the 1 minute I can spend on this slide. But those that do have that background, those are our definitions of solution space and weight function space. Basically, in a nutshell, a function space simply means you break up the mesh into cells, and on those cells, you interpolate with some polynomials the solution over the interior of that element. That's really all the fancy math set grouping stuff is in the other slides, in the other boxes in the slide. Okay. We're dealing with compressible flow. Compressible flow can have shock waves. The previous form that I showed you will generate oscillations around shocks. So we add yet one more term called discontinuity capturing that has this, rather complicated matrix multiplications to form effectively an additional viscosity that controls oscillations near shocks. So key features of this are that it should act only in the direction of the gradient so that it doesn't diffuse, be overly diffusive to the method. It should be proportional to the residual so that as you refine the mesh, it goes away. And that's really all we need from that slide. When it works, you get shock solutions like this, fairly crisp resolution of discontinuities, like you see in the upper right box at about 0.85. That's where the shock wave is sitting. And with only a couple of points interior, the stars are at points of the mesh. you may say, well, some of the other stuff looks smeared. Those are actually different types of waves, which are not discontinuous, but they are conserved and properly accounted for with that term. Okay, if you're still awake, that's it for equations. We're now just going to talk in words about what we do. So here's an overview or the takeaway from all the previous 11 slides. So PHASTA is a massively parallel MPI-based Navier-Stokes solver. It can solve compressible or incompressible laminar, turbulent, and unsteady flows. I told you it uses a finite element discretization in space, which means it can handle complex geometries. Its order of accuracy is the mesh spacing to the k+1 power. K is the polynomial order, so if we're using linears, it's second order accurate. If we're using quadratic basis functions, it's third order accurate, and so on. It's minimally dissipative, which is key to resolving turbulence, as we'll see in a moment. It's fully implicit in time, meaning that we can choose a time step that is based on our physical needs, not based on stability needs. And I don't have time to get into the details of why that's complicated, but it's a lot harder to make an implicit CFD solver scale than it is an explicit one, and yet it's worthwhile. PHASTA can also use mesh adaptivity, which means that we can basically adjust the position of points and how they're connected to make the grid match our physical needs, and that can also be anisotropic as is needed for boundary layers. We'll talk about a few different types of scale resolving simulations. DNS stands for direct numerical simulation. LAS stands for large eddy simulation. RANS stands for Reynolds average Navier-Stokes. And then there are hybrids of those. We'll show in a moment some scaling plots that shows that this solver strongly scales to 768K cores, or up to 3.1 million MPI instances if we are running on multiple MPI processes per processor. And it's been applied to a number of flows that of different type, the largest being scale resolving turbulent simulations. Okay. How does PHASTA take that finite element formulation and efficiently work on a parallel computer? So there's really two stages. We form equations and we solve equations. So this slide really recaptures everything that we did from before. That is, we have a partial differential equation, L of y minus, sorry for a different symbol, different shaped F or S. We apply the stabilized finite element method, which breaks it into volume integrals. We then approximate those volume integrals with quadrature. Quadrature just means that we're sampling that integrand at points inside of each and every one of those cells. And we had a boundary integral term, so we also have to do one dimension lower integration by quadrature on, if it's a 2D mesh like I'm showing, it would be on the edges that are on the boundary of that domain. After we've done that quadrature point evaluation, we're left with an algebraic system of equations. I'm leaving out the time discretization, but that's just an OD integration step that happens in between quadrature and assembly. And in the end, we end up with an AX equals to B problem. Secretly, we end up with an AX equals to B problem for each linearization. Those are nonlinear equations, so we have to do this multiple times. Okay, so that's the equation formation. That is the building of A, the left-hand side, the building of the right-hand side B, and X is our solution variables that we're trying to find. So then the other key work step is equation solution. That is solving for X given A and B. We're gonna use a GMRes type solver, which means the first step is that we assume the X is 0. So that means that P is equal to B. And then GMRes is basically going to require us to do a bunch of matrix vector products, A times a test vector P to get a Q. orthonormalized Q, and to build up basically a basis for the solution in terms of those types of operations. So how do we do that? We're going to decompose that domain into a partition. In this case, I'm showing breaking it into 3 parts, part A, part B, part C. And we'll have to keep track of the degrees of freedom that are on the boundary. And what we'll basically do is let each process do the equation formation for its part. So in this case, we'd have 3 processors, and the 3 processors would, processor 1 would do part A, processor 2 would be part B, processor 3 would do part C. And that's embarrassingly parallel. That work can be completed without any communication. However, the nodes that are shared amongst these processes will not have complete information until we do a peer-to-peer communication. That is, basically, we have to pre-process the hollow dots in this picture and how they're connected to the solid dots in some part. And so basically, there's a peer-to-peer communication that has to take place to make that complete. Okay. This may sound like it could get out of hand, but even when we get up to 3.1 million processes, this asymptotically bounds to about 40 peers for each of these processes. And this has been shown to scale well. We'll see in a moment the scaling operation. Now, in the equation solution part, it's a little more complicated. We can still do those matrix vector products on each processor, and we can still do the communication. But the really tricky part is that after we've done the on-processor dot products, a dot product won't be complete until it's done over the whole mesh. So there is an MPIL reduce step, and that's really where scaling becomes difficult. On the scale of the problems you're going to be solving on a few nodes and a couple of hundred processes, this isn't a big deal, but this is a very big deal for much larger process counts. Okay, so let's go ahead and look at some scaling results. So this is a 92 billion element mesh, which means that there's about 8 billion mesh nodes and about 64 billion degrees of freedom in the system being solved. And we're going to solve this on ranging from 256 to 768K cores of, this was on Mira. This was a Blue Gene machine that's been retired since I made this slide. That allowed 1, 2, and 4 MPI processes per core, which is the way we got up to 3.1 million processes. So we're going to talk about strong scaling, which means that we take the time on the base configuration times the number of cores, and we divide that by the other configuration. So if we get 1 with 1 MPI process per core, that means it's perfectly scaling. If we get any acceleration from adding more processes per core, then that number will be greater than 1. Our baseline is 256K, 92 billion elements, and this is the scaling information. What we see is that the equation formation in the lower left scales very well with 1 process per core, the blue curve. We get some acceleration with 2 processes per core, the red curve, not quite a factor of 2 and not quite a factor of 4, but we still get some acceleration by overloading more MPI processes per core. In general, that won't be true on most architectures. Most architectures don't get acceleration from overloading processes, but Blue Gene does. The equation solution is actually super linear. That is, moving up in cores, it actually takes less overall computational time, and that's because of better cache performance. On a different architecture machine that still exists, Theta is a Xeon Phi. Again, equation formation scales well, equation solution, and the total scales well. I'm going to go pretty quickly through an application. This is a flow control on a vertical tail. There's the real vertical tail we compared to in the wind tunnel. That's, that's modeled scaled model of a Boeing 767 vertical tail. You can sort of see the rudder. Now you can't see it very well in this picture, but when I added the cartoon, this vertical tail was configured with 12 synthetic jets, and those synthetic jets expel and ingest air through a piezoelectric disc vibrating at 1600 hertz. And this is meant to try to help the flow stay attached at the larger rudder deflections shown in the picture. So this is a movie of a simulation from that, well, a movie from that simulation. And there are, in this case, about 10 billion elements being solved hundreds of thousands of time steps. In this particular case, only the 5th jet is active. You see other jets are quiet. And you see the rich flow structure that's created by turbulence. And just to show you, it's not just pretty colors. We match the experiments with 1 jet blowing, with no jets blowing, and with all 12 jets blowing. I'm just going to skip over this slide because I'm running short on time. And this will be the last slide. This is a higher speed flow. This is a Mach 3 flow over, my movie's not starting, over an initially flat plate that then's turned upward. When the plate is turned upward, it creates a shock wave. So again, this is about Mach 3. The upper picture is showing vorticity contours within the boundary layer. The lower picture is showing Mach number, and we see the turbulence flowing and being altered by the shock wave. Okay, so that's it for my slides. I'm going to stop the share here and switch over to a different share, hopefully. Okay. Okay, so are you seeing my virtual desktop of my lab computer?
Yes.
Okay. Let me try to move something out of the way here. Okay. So that URL I gave you should take you to a page that looks like this. I guess actually it may take you first to a page that looks like this. And then if you click on PHASTA, you get to this point. So if you do get clone and you go over here to code, and I suppose you probably all know how to do this, but I'm just gonna do that, and that has downloaded the source. So if we take a quick peek at what we've got, like any good cooking show, I've got some stuff in the hide directory that if we run out of time or something doesn't work, can pull out what I practiced this morning. Okay, so I'm not going to go through all of the source here, but just at a high level, we use a Cmake system, so there's some Cmake files for you to be concerned with. The primary source is in PHSolver, and within PHSolver there are 3 libraries that are not libraries. There are 3 folders. One called incompressible, one called compressible, and one called common. When we go and build up the compressible solver, we won't need that incompressible folder. I think I'm going to restrict, well, I am going to restrict this app activity to the compressible solver because it has no dependencies on external software that can make things more difficult. Okay, so going back up to here, I typically make a build directory. I CD to that build directory. So, oops, actually, we need to do something else first. If we want to get some of the test problems. So what that did was downloaded a tarball, PHASTA chef test tar.gz. Let's go ahead and extract that. So we'll come back to that in a moment. But there are 4 cases there. We're only going to cover one of them today. And actually, I'm realizing that this may be a little bit small for the recording. So let me make this a little bit bigger. So in case you missed it, this is what we've done so far. We cloned. We took a little peek of what's inside of PHASTA. We did a build. We got our tarball. We untarred it. And we looked at some of those cases. And now, and I didn't really mean to go up another directory, but I guess it did. Okay, so let's go ahead and build the code. So in terms of environment, before you build, you need to have access to a few things. You need to have some form of a compiler, and you need some form of MPI. This is a pretty old GCC compiler. Sometime today, I'll make sure that all the updates that are needed for 10.2 or earlier are in the code. I think right now, if you try to use it 10.2, there's a couple of routines that need to be updated. And I just haven't merged that back into the master yet. Okay, so I've already sourced my environment, but you need to get some sensible answer from which MPI run and some sensible answer from GCC. With that, you also need to set up a Cmake configuration file. So for the way that I've got things set up, what's in the wiki is workable. So I don't like to be having to go back and get this all the time. So I'm gonna paste it into a little helper script. So as the note says, this is a very bland version that we're doing here. Basically, we're setting up, telling Cmake what we want to use for compilers. We're asking for a debug build. If you're going to run cases and for performance, you want to change debug to release. We're not going to build the incompressible solver. We are going to build the compressible, and we're going to start off without PET-C, because building PET-C is another project. So I'm just going to source this file, which basically gets Cmake acquainted with what we downloaded. And then I'm just going to make, you can just say make, but it's going to make a whole lot of extra stuff that for this demo we don't need and just takes time. Yes, actually, I will say more if we have time at the end about PET-C and SVLS. But for now, we're just building what we call the native or built-in equation solving library. They are just equation solving libraries. They're alternatives to what we've hard coded. Okay, so let's go ahead and build this. Oops, let's get the mouse in the right window. Okay, so if we have succeeded, a couple of things have happened. In bin, we have our executable, and somewhat importantly, during the build process, we've copied out of source a file called input.config. It's, if you will, all the default settings for the solver so that you don't have to, in your solver control file, set everything. Okay, a little more on that in a moment. So we've succeeded with building. And oops. So let's go ahead and try to run a case. So I'm going to go over to PHASTA chef tests. Of course, you can redo the tarball whenever you like. I am just in the habit of keeping what I downloaded pristine and safe. And so I'm going to copy one of my cases. To the one that we're going to demo. So what is in this tarball for you? There is a histor.ref, which is the history of the output of the code when it was run sometime in the past, that we can cross-check that we're getting a similar or the same output. As you change the code, there may be some small changes, but there shouldn't be large changes to what you get as output from the code than that. So I say that, and yet it is going to be different because I've changed the format of the output. But the basic look and feel of it will be similar, as we'll see in a moment. I will probably update the tarball to be consistent with current outputs. All right, so let's go back to the demo. So the primary input is from solver.imp. So I'm going to copy, we're going to run the native case. If you call it solver.imp, then you don't have to tell the solver the name of your input file. So that's what I just did. If we take a quick peek at this, this gives things like, well, are you solving compressible or incompressible? Are you including viscosity or not? What sort of turbulence do you want? How many time steps do you want? And this goes on, what's the size of time steps and so on, and then properties and so on. We don't have time to go through all of the inputs. If we have time, we'll come back and go through more. But it's set up with sensible inputs. So that's what I'll call the text inputs. But these directories give us the mesh and the initial condition inputs. So this is, if you will, the big data directories, whereas this is the small parameter input files. So we have two different data formats. We have what's called Posix and Sync Io. Posix is going to make one file per process. Sync Io allows us to bundle multiple files, multiple parts into the same file, which, as you can imagine, becomes important. If I'm running 3.1 million parts, there's not really many file systems that want to see 3.1 million files inside of a single directory. So that's to handle that issue. But at 2, it doesn't really matter. So the code expects to find a directory with that name. And sorry, that's a directory, so we need -r. So let's look at what's in there. So it's a 2-part case, which means that there's 2 geom.bc files and there's 2 restart files. The restart files have a part number after the last period, and they have a step number between restart and that. So this is step 0. So if I more numstart.dat, I need to copy numstart.dat into this directory for it to run properly. So it'll be a later demo that I'll show you how to change the number, or I'll show you the pre-processing that prepared these files. But today we're going to deal with, prepackaged food, lunchable form instead of the make your own inputs. But basically, we have to have basically 2 times the number of processes plus 1 files. We have to have 1 file that looks like this, and then as many restarts as we have processes, and as many geoms as we have processes. Okay, we're now ready to run. So specified number of processes. Oh, we're not ready to run. I told you about that input.config file. We have to set an environment variable. That points to where that file sits. The executable is going to look for the input.config file at whatever environment variable you set here. So we set the build up so that it always copies a consistent input.config with a certain source hash. So if you do this step, you'll always be safe as long as you do the next step, which is sort of a safety check. So now I'm making sure that that is the executable that I use is consistent with its configuration file. Now, if I wanted to run one of these other solver.imps, I could add that name here. But because I already copied it to solver.imp, I don't need to add anything more. Okay. So that there's some time for questions, I'm gonna not spend a lot of time explaining. Well, I'll spend a little bit of time explaining it. This is doing 2 time steps. You see number 1 is repeated 4 times. It's doing 4 iterations. And this is showing you the residual, or how well we're satisfying the PDE after it's actually at the beginning of the first iteration. At the beginning of the second iteration is here. at the beginning of the third iteration is here, and fourth here. So you see we're driving that residual closer and closer to zero. This is more than enough convergence on a given time step, and then we move on to the next step. So again, we're solving a transient flow here. Okay, so really quickly, if we want to look at that solution, I believe in incompressible adapt, I have a pair view PHT file. I'm just going to copy it over. This always requires a little bit of customization. That is, this needs to point to the right directory to find the files. It needs to point to a time step that exists. We ran 2 steps. So if we ran lots of steps, we could through the XML set up looking at lots of steps and their increment factor. I did do one run earlier. And this says what fields do we want to look at. This is pulling out of restart.2. Well, I should have shown you that out, but we'll do that in just a minute. Actually, let's skip that. So before we had geom files and restart.zeros, now we have restart.1 and restart.2. So we're writing every time step into a restart file with that solver on it. You can control to write more or less frequently as well. We also got an echo.dat and some forces.dat and some other files. That histor.dat is what sort of matches that histor.reference. The columns changed a little bit. We reported the residual 2 different ways now, but it's basically otherwise the same. So this is again checking reproducibility. Okay, real quickly. Pair view has a native reader for PHASTA. So I can look at my mesh. So this is a fully unstructured mesh. This is a simple channel flow test case. So if I look at velocity, I see the flow has begun to come in on the left, and 10 or so time steps it will fill up the domain and make a channel flow. Basically, the top walls no slip, the bottom walls no slip, the left is inflow, the right is outflow, and this is, if we rotate, we will see a 3D domain. It's just really skinny in the 3rd dimension. Okay. So there's lots and lots of stuff, but this is an introduction. I guess I want to leave some time for questions, so I'll pause. So that I'll answer a little more verbosely the one question that I have already seen in the chat, which is, explain more about SVLS and PETC. They are linear equation solver libraries. SVLS is a solver, the open source solver that's available for the incompressible code. PETC is more than a solver. It can do a lot more than solve, but one thing it can do is solve equations. PHASTA basically can assemble the equations into the form that PETC expects, and then PETC can then solve the equations as an alternate to the native GMRes solver that's built into the code. The advantages to that are that PETC has a much richer library of preconditioners, but it's how I will say it has similar efficiency to PHASTA with regard to its native GMRes implementation with block diagonal preconditioning, which is what PHASTA has. I'm not seeing any other questions in the chat. I can go ahead and fill the last 10 minutes with other demo, but if we have questions out there, I want to give you some time to ask them.
I have a question.
Sure.
Is there any difficulty with bringing the visualization up in peer review? This is more just a traditional peer review install that's needed, or is there anything special needed for that?
So I don't think you should have any issues with peer review. This is I've used several different ones. This one's using 5.4.1, but I've used 5.9, which is the current release, or 10. I guess 5.10 is the current release. If you hit an issue, then certainly post a question. But the most common problem to have is small typos in well. So I guess if your problem is getting peer review to launch, I can't help much. But if your problem is getting it to load a PHT file, I'll tell you that it's very easy to make a small typo in here. You need to cross-check the paths here. You need to make sure that the number of pieces match and that you have the time steps that you're looking for. So this is actually loading that restart, the GMBC file and the restart.whatever step number you say here. So you also obviously have to ask for fields that exist in that. And right now I'm pulling out of a solution field and I'm telling it, what index in that field that it is here. Okay. So there's a question about GPU. The GPU is in progress. It's not in the master. If we get it to a releasable point, I will update, what branch to download. But at this point, it's been the major development for most of my summer, getting this running efficiently on a GPU. So for now, I think we had said that we're going to say that you should plan CPU only, because we don't know whether the GPU option will be ready in time. So Yi asked the question, can we generate inputs that run on more processes? Yes, but as I tried to pull this together, as you can see, it was a whole lot of information just to get to this point. So what I plan to do is make recordings, Zoom recordings, and then post links to those for how to build the tool which partitions the mesh into more processes. And we can probably work even this case on more processes. There's basically a preprocessor that takes mesh generation code and some other text information, and then you tell it how many parts you want it broken into, and it creates what we used as proc case directors. But then from here forward, it would be the same. You just would change MPI run-np to however many parts you broke your mesh into. So yes, Mr. Yen, that's exactly what I'm saying. We will replace well, I will provide a tutorial that will show you, will give you some other inputs, and those inputs plus the preprocessor will break it into more parts. So right now, this PHASTA chef test is just to get you acquainted with running the given cases. So I think it's probably worthwhile to go to those inputs. Oops. So you might be tempted to take a look at this file without the aid of ParaView. And what you'll see is that it's a mixture of, well, it's a key value store format. That is, there's a string solution, and then there's some information about the size of that, and then there's stuff you can't read. So binary. So so you can see the available fields by searching. So there's solution, there's time derivative of solution. I guess that's all there is in this one. And similarly, in the geom files, they're following the same format. There's certain ASCII text header information. And then there's, for example, the coordinates, that is the points of the mesh. There's an array that keeps track of the connections on the boundary. That's in the IO work array. There's the connectivity array. There's basically the other data structures are, again, a flat text header followed by the data associated with that. And again, the idea is not that you ever edit these. I'm only going into this to show you what they look like. In the follow-on to this, again, the pre-processing tool will create these files from a given mesh and its attributes. As terms of attributes here would mean where do we want the boundary conditions to be and what values would they be, and so on and so forth. So absent questions, I'll go ahead and say some other things that are commonly asked questions. You know, what is this output? I already said that the first column is the step number. The second column is elapsed time. The third column is what I referred to in the opening slides as residual. That is, how well is the PDE being satisfied? This will always be 0 on the first iteration because this column is tracking in terms of decibels how much this number has gone down. So unsurprisingly, 41 decibels means that this iteration is about 4 orders of magnitude lower than we started. And we see that it's gone 10 to the minus 7 to 10 to the minus 11. The next two columns are just a different measure of that same residual. One of them is preconditioned, one is not preconditioned. This will be an important vector for you to take a look at, and I guess we're out of time. This is how many Krylov vectors were used in the solve. This directly affects how much time it takes to solve. Okay, I don't know. I think this is our hour. We did start a couple of minutes late, but I think hopefully this is enough to get you started, and it won't be long before I post the video on how to make different numbers of parts. So there's a question about proprietary. You notice I didn't cover that. That probably means that you found some tutorial pages that do cover that. We're not going to be using SimModeler. I'm going to show you an alternate route for the question that's in the chat that avoids. We will need to build up Chef. Chef will need score at core, but we won't need SimMod Suite or SimModeler.
Okay, thank you so much, Dr. Ken. It was an excellent talk. I would like to thank all of you for attending this call, and I hope to see all of you in SC22. And have a great day.
Thanks.
Thank you.
Bye-bye.
Bye.
Thank you.
Thanks, Ken and Maya.
You're welcome.